at the EC and RBCCPS IASC. Today's talk is by Professor Manjesh Kumar Hanawal, and he will be speaking on learning optimal beam directions in next-gen wireless networks, a fixed budget stochastic bandit approach. Professor Manjesh Kumar Hanawal completed his BTech degree in ECE from NIT Bhopal in 2004, Masters in ECE from IASC Bangalore 2009, and PhD from INRIA Sofia Antipolis and University of Avignon, France in 2013. After 2 years of postdoc at Boston University, he joined industrial engineering and operations research at IIT Bombay, where he is an associate professor now. During 2004 to 2007, he was with CARE, DRDO, working on various security-related projects. His research interests include communication networks, machine learning, and cybersecurity. He is a recipient of the Inspire Faculty Award from DST and the Early Career Research Award from SERB. He has received several research grants like Matrix from SERB and Indo-French Collaborative Scientific Research Program from CEFIPRA. His work received the Best Paper Award at ComsNets 2018. Before we move on to the talk, we would like to request the online audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the online audience to please keep your microphones on silent for the duration of the talk, except while asking questions. And for questions, you may unmute yourself and ask Professor Hanawal, or you can type them in the chat box. Over to you, Professor Hanawal.
Okay, thank you. First of all, I would like to extend my thanks to CNI for asking me to give this talk here. And it is wonderful to connect with people associated with IASC as always. Okay, so today I'm going to talk about some of the work I have been doing of late in developing some learning algorithm for the next generation wireless networks. So in particular, I'm going to talk about how to use bandits for this learning aspects. I hope my voice is audible clearly. Or should I speak some more louder?
Yes, Professor, it's clear.
Yeah, okay, great. So this work is supported by grants from SERB and a center called the Technocraft Center for Applied Artificial Intelligence at IIT Bombay. So most of the work is done with my PhD student, Devmita Ghosh, who is a IIT Bombay Monash Research Academy student. And Nicolas Letanova was earlier with Monash. Now he is at Indianapolis University in Russia. So just know what happened. Okay, let me make it full screen. That's better, I guess. Okay, to get started, this is something all of us know. Now, millimeter waves are now proposed or already being used as something which provides us high bandwidth and also high speed communication, especially 5G is using this millimeter wave communication, and also it supports all the low latency applications. However, there are disadvantages with millimeter wave communications, being high frequency signals or a low wavelength, they suffer a lot of attenuation. So because of that, they can't travel long distances, and also they can't be used in a dense deployment because they get very heavily attenuated. Now, to overcome this, people have proposed to do concentration of the signals by forming beams and then look for that beam pairs which gives you maximal received signal strength. However, now this adds an additional layer of identifying what is the good beam and identifying that beam pair which gives us maximum signal to received signal strength. And if you make any mistake in identifying this good pair, and if there is any misalignment between them, all the gains we're expecting in terms of the throughput may get lost. So our throughput may suddenly drop from gigahertz, which is expected, to maybe just like a few Mbps. And also in this case, the learning itself could be involved because where is the receiver, transmitter may not know a priori. So it has to figure out where is the receiver, and then they have to mutually agree upon a beam pair to transmit. So these are the additional complexity that brings in if you have to use millimeter wave communications to increase, to get a better bandwidth and achieve the promised latency and throughput. So here is the quick summary. Like, I mean, yeah, we have all this space can be divided into the beam, and the signals can be focused in this beam directions. And now to achieve the best possible signal to noise ratio or signal strength, we have to make sure that transmitter and receiver beams are in such a way that they are almost like making a line of sight path. Now further, if you look into the signal strength as a beam index, like maybe we can divide my whole space into small angles and we get multiple beams. And if you look into the signal strength as a function of beam, we may see that the signal strength may vary as the beam index. Maybe some signal strength are very high and then it falls down sharply as we move away. And it may happen that there is some non-line of sight component, which again increases my beam sight, my signal strength. So what is important to notice is, so there is a pattern here. Like when I increase my beam index, maybe my signal strength keep on increasing at some point, and as I move away from that, again my signal strength keep going down. So there is an increase-decrease pattern, and this is pretty evident on the line of sight path. But even on the non-line of sight path, this could happen. And most of the time, because of this nature of the millimeter wave, the signal strength received on the non-line of sight path is going to be almost negligible. Maybe we can ignore that. Maybe we can focus on this portion where as I move from the left side, my signal strength increases, and I move away, my signal strength goes down. Now we have to learn this. Where is the point, which is that beam, which gives me the best signal strength? Now this leads us to a learning problem, how to identify this. When it comes to learning, Multi-Armed Bandit framework is one of the natural framework. And people have studied this particular structure and given nice theory with algorithms, both upper and lower bounds, when in the setting of something called cumulative regret minimization. And this structure I called is known as unimodal structure or multimodal structure in the beam strength, and this has been exploited nicely. But in the cumulative regret set. However, this cumulative regret setting may not be very much useful all the time to use in the wireless network, because cumulative regret setting has this natural property that there is a continuous exploration going on. It's not that we will commit to one particular arm after certain rounds of initial run. Because of that, however far you are into the algorithm, you may still end up playing the suboptimal arms. And if you happen to play a really bad arm, you may actually, your connection may get disconnected because of outage. And also, this continuous exploration is also always not good, because you are basically switching between the beams, which is undesirable from any protocol design point of view. So because of this reason, we want to move to a situation where, yes, we want to exploit this unimodal structure, but instead of the cumulative regret setup, we should go something which is more deterministic, so that it is more aligned in the protocol design. One such thing is this fixed budget pure exploration. So in the Bandit literature, again, this fixed budget pure exploration problems are also well studied. But here you preset the number of rounds you want to play. And after that many rounds, you are going to commit to an arm or an action and keep on playing that in the remaining time. So that is what we want to see that. Now, fine. There is a unimodal structure in your beam signal strength. You want to exploit it. But what is already there in the literature, cumulative regret, that may not be always good in the wireless setting. So we need to see that how we can use the fixed budget pure exploration setting and exploit this unimodal structure. Okay, here I have put the channel model that we are going to consider here, or the network setup we are going to consider. We are going to assume that the transmitter has equally spaced k-phased array antennas so that it can beamform. Whereas the receiver, for time being, we will assume that these are all omnidirectional, like the receiver is listening from all the direction and it is not beamforming. But when the receiver is also beamforming, we can extend this. But right now, let's focus on the transmitter part. The learning is focused on the transmitter part. Now, the channel model is pretty standard. We are going to say that there are k beams. These beams are already designed. Somebody has already designed the beams and provided the necessary code books for you. It is already with you. And there are k beams. And if you are going to if you are going to use beam k, so this is your received signal. So BK is the beam you chose. H is going to denote the channel characteristics, the complex gains of the channel, and P is the power with which you are going to transmit, and N is the, as usual, additive noise here. And now what we would be interested in, the received signal strength, which is the square of the absolute value of this YK in an expected sense. Okay, and that value, we are going to denote it as mu k. So mu k denotes the mean received signal strength. And I would be interested in identifying a beam which gives me this best beam in terms of its mean received signal strength. So my goal is to identify an k star, which is the best among mu k's, and that beam, associated beam, I'm going to denote it as bk star. Now, question comes, okay, fine. This is a classic setting we have. We have the arms, which are now beams. They have their associated mean received signal strength. We need to identify the best one. Then the question comes, how to use the unimodal property. So before we start how to exploit the unimodal property, the formal definition of unimodal property is given here. Unimodal property says that, there exists always arm, which is the optimal arm. So your values of the mean keeps increasing till that part, and then it will start decreasing. So there is only one mode here. So the peak is happening at one point. Now we set our goal as identify this best arm within a given budget with as much high confidence as possible. So from the protocol point of view, this is what we should keep in mind. Suppose my protocol is designed in such a way that over a period of T rounds, it has been allowed to do the exploration in the first alpha T fraction of the time. And after that, it has to decide which beam it has to use. And after that, it should continue to use that till that block period is over. So each block here, which is of duration T, has this channel estimation phase and the data transmission phase. And in the data transmission phase, I don't have the luxury to keep changing my arms. Like I have to stick to one arm and continue data transmission. And like this, there could be many blocks, and I can repeat the process of channel estimation in each block. And once I complete my channel estimation part, in the remaining rounds of that block, I commit myself and continue the data transfer. Okay. Now, by putting it in such a simple fashion, I mean, our maybe protocol design is simple. All I need to do is, okay, what is that alpha, the algorithm? So that algorithm will keep on exploring the beams, and after that, it will use one arm to do the data transfer. So there is a kind of determinism here, like after exploration, I know which arm to use for the data transfer.
Sir, I have one question.
Yeah. Please go ahead.
So in the exploration phase, the channel estimation phase, is every beam or every arm explored?
No, that is adaptively done. Of course, each arm will be at least seen once. The adaptation will force you to look into that. But if you are asking all of them are looked into equal number of times, that's not necessary.
Okay. So it may happen, I mean, initially for few phases, this it will be the suboptimal arm, whatever you choose, and data transmission phase is done. That will be suboptimal, right, for the initial few phases? Yeah.
So here I will be just exploring. There is no data transfer here, so I don't worry about data transfer at all here. Here I will be exploring and identifying which arm has the highest mean received signal strength. And from this point onwards, I will use it.
Okay.
So here I'm just exploring, and I'm making the decision of which one to use only at this point.
Okay.
Yeah, maybe here I can pause and see if there are any other questions. Should I see also on the chat box?
I don't see any questions in the chat box.
Yeah, so whatever I said, this what happens in one block, and if the, let's say, the environment is not stationary or something, then we can repeat this in every block, and my algorithms may use a different channel for data transmitter in each of these blocks. Now here, a policy is any strategy that selects an arm in each arm slot given the past observation, and the exploration budget is already given to the algorithm. That's an input. And B is the set of beams or arms we have. And in each round, the algorithm is going to select an arm to play based on the past history. So it is making things adaptive by using the past history. And the feedback here is whatever the policy pulls and beam, it will get to see the received signal strength for that. And based on that, it has to decide what is the action it is going to take, what is the arm or beam it is going to play in the next round. Now, our goal is to find a policy pi such that my probability of making a mistake is minimized. So as I said, K star is my optimal beam, and the K hat alpha T is the one which is returned by my policy pi. That the probability that my policy does not return the correct arm, I want to minimize this policy across all possible policies. So this is my goal, and I want to learn such a policy. And here, as I said, this K star pi alpha T is the arm that is output by the algorithm after it completes its exploration course. Okay, now let's understand how this algorithm works. We all know about how the classic UCB algorithms work, right? Like there is always we maintain some estimates, we maintain some confidence about those estimates, and by appropriately combining these estimates and the confidence in it, we identify which arm to play optimistically. But where are here there is some structure in the means and we want to exploit it. So the classical UCB algorithm, they does not exploit any structure in the mean arms. Okay, and not only the cumulative regret minimization, the ones which actually does this pure exploration algorithm like LUCB or KLUCB, they also don't assume any structure. But here we are having a structure. So we need to be doing something differently than what they are doing. Okay, so for this, what we're proposing is an algorithm. It is based on something called elimination. And our elimination is slightly different from what is there in the literature. So many of you might have heard about algorithm called successive elimination, like where after some time, half of the arms get eliminated. But here, instead of doing that, we maintain whatever the arms we have. From them, we partition our region into basically 4 parts. And at the, sorry, actually 3 parts. And at the end, we are going to throw away 1/3 of it. Okay, let me take you through this algorithm. So T, number of round, alpha, and K are the inputs. And we are going to run this algorithm in phases. And that phase is denoted by L here. And in each phase, we are going to select 4 arms from whatever the arms remaining in that phase. So one, for just pictorial representation, let's say we have some bunch of arms, which is denoted as BL. And now I have to go to BL plus 1. How I do this? From the BL, I choose the leftmost arm, which is denoted as KM. That is the first beam in my set BL. And I will take the last beam in my set KN. And also take 2 intermediary beams, KA, which is representing 1/3 of the number of beams, like which is 1/3 away from K3 in terms of the number of beams, and another arm KB, which is 2/3 away from KM in terms of the number of beams. Now I have selected these 4 arms, and each of these 4 arms, I am going to play NL by 4 number of times. These many samples I'm going to collect for each one of them. Why this is done? Yeah, it is done in such a fashion so that things add up and we are within the budget, and also the estimates we have is telling something reasonable about the quality of this beams. So NL for each phase is given like this. I mean, I will not go into the details. What we'll do is, after the foams arms are selected, I will see which of them has the highest mean. Suppose it so happens that among the 4, this guy happened to be the highest mean, then I will going to retain all the arms which are between KM to KB and throw away this part. So basically, I have throw away about 1/3 of the arms in this case. Okay, so depending on where is your peak is, you may either end up throwing this much of the portion or this much of the portion, like 1/3 of the portion. Now, after you keep on doing this, at the end, when you reach the L plus 1 phase, whatever the arms you have, you just sample them. Again, there is how many samples will be again given by this expression NL, and you take the best among them and output that as your arm recommended for data transmission. Now fine, this structure looked weird. Why is that we are doing this? So it so happens that if you do like that, one can guarantee that the optimal arm sorry, the arm that is output by the algorithm, it being not correct to be the optimal arm, is the probability of that is upper bounded by like this. You see that like that error is going exponentially fast down in t and some quantity delta square here. I want to highlight a little bit about this delta because this delta is not the same as a suboptimality gap that we come across in the standard bandit theory. So here delta is the gap between two neighboring arms. For example, if it is just like a flat line, the delta is going to be 0. So our result is not useful there at all. So whenever there is an increasing and decreasing pattern, and if there is a sudden increase and sudden increase, this delta will be high, and this is what it is capturing. Okay, now if you see these 4 terms here, why these 4 terms comes? Because again, we are considering the various regions, right? From which portion the arms get eliminated. Depending on that, we get this different region, and we bound the error probabilities of each of those regions. Now, if we look to this error, this is of the order log k exponential minus alpha t delta square with some constant here. Now, the question is, how much we achieved by exploiting the unimodality. So we can compare this bound with the case of unstructured bandit. And in the unstructured bandit, the best bound is shown to be this quantity, which is achieved by successive elimination algorithm. If you see that everything remains the same, except for the fact that here I have delta square, but here it is H2, and there is an additional factor of log k here. And here H2 is something called a complexity parameter that actually depends on the suboptimality gap, and that is different from this delta. So delta here is the, here as I said, this is the minimum gap between the neighboring beams. So the point to note here is this log k factor which appeared here does not appear here. That means the dependency of this error exponent on the k factor is gone when you exploit the unimodal structure, whereas it remained in the case where you did not exploit any structure. So that is the gain we are achieving in terms of the error exponent by exploiting the unimodality through our algorithm. And this is, we can also show that it's not that just an artifact of our algorithm. When you derive a lower bound for any algorithm which exploits this unimodality, you can show that there also the exponent does not depend on log k. I did not put the details of a lower bound here, but yeah, the lower bound appears just like this, but this delta is replaced by H2. The fact remains that the lower bound also does not depend on log k factor in its error exponent. So in that way, by exploiting unimodality, we have attained a tighter bound on the error exponent, but optimality is still not there because our bound depends on delta, which is not same as H2. Okay, now I want to take you through some quick numerical simulations. There are several algorithms, as I discussed, for the pure exploration problem, and some of them even has explored unimodal bandit. So some of the algorithms are sequential halving, linear search elimination, and recently some algorithms have come like named hierarchical beam alignment and hierarchical optimal sampling using unimodal bandits. So here are some plots like how our algorithm compares with the others. I know that these figures are cluttered, but what I want you to focus on the summary that is written at the bottom. So the nice thing about our algorithm UB3 is that it identifies the best arm with probability more than 95 within about 200 budget, like within about 200 rounds. Maybe you can think it like in a wireless network, maybe I can just use about 200 pilot signals to identify the best arm when the number of beams is 16. Whereas all the state-of-the-art algorithm that we discussed, they within the same budget, they could provide you only the probability of about 88%. So under the same budget condition, our algorithm guarantees a much better error probability compared to the state-of-the-art algorithm. And this also translates to better throughput. Now that we are able to identify the best arm in a fewer number of samples for a given, if you are going for a given confidence, output alternatively, like you are able to achieve identify the best arm with good confidence with a smaller number of rounds. Now you have more slots for data transfer, and obviously your throughput is going to be better in this case. So these are some throughput graphs which we have plotted for different distances by varying the distance. And you can see that our UB3 consistently gives a better throughput compared to other algorithms when the number of beams are about 64. Okay, so in summary, what we observed is UB3 can improve throughput by about 45% compared to HBA, which is the most recent algorithm which is developed for this exploiting unimodal bandits, and it achieves actually better than 15% compared to the HOUCB, which is the most recent one. Okay, so let me pause here and see any questions so far that I have discussed on the unimodal bandits and our algorithm UB3. Next, I'll be switching to another topic. So before that, I want to see if there are any questions here.
So I have a question.
Sure.
So basically, suppose if I consider an hierarchical based beam alignment, then essentially the fixed budget constraint that you're imposing in the bandit translate to, for example, the depth, the maximum depth of the tree that depends on the number of layers in which you want to hierarchically search over the beams. So then in such kind of a constraint, can I not also equivalently adopt an hierarchical based approach to solve this problem? I mean, what benefit does a bandit based approach gives over an hierarchical based approach is my question.
No, like first thing is we are observing noisy observations, right? So we have to learn it. But in the hierarchical beam algorithm you're talking about, it is again with the noisy observation.
Yes, yeah. So basically, even hierarchical, you do, in every stage, you basically filter out or cut down the beams over which you want to, sounds. That's why I was curious to understand what bandits is additionally offering.
No, like HB algorithm, as I know, it is also using some kind of bandit theory there itself in terms of using a confidence bonus and all. But the way they are doing and the way we are doing by dividing the region into 3 parts, that is different.
Okay.
I'm not sure, like your specific question, like about using the bandit, are you asking me how differently I'm using bandit than it in HBA?
Yeah, I think that was my question.
No, at this point, I mean, I'm not sure I'm completely have the right answer for you. All I'm saying is, yeah, the way we are doing is whatever the current, I am eliminating they're possibly eliminating the branches as per the tree, but here we are eliminating some portion of the arms itself, like 1/3 of the portion of the remaining, whatever the arms I have, they get eliminated. And based on that, I am further choosing 4 arms from the remaining and continuing this process.
Yeah, sure. Okay, thanks.
Okay, so another application I want to talk about is something called holographic Metasurface transceiver. Now, we all heard about a massive MIMO, where we pack large number of antennas and try to get beams, sharp beams in the direction we want. But the challenges there are, like, maybe the cost of the hardware is high, and also implementation of the increasing the antennas arbitrarily is maybe not be always possible. So because of that, maybe there are other ways we want to use it. And this holographic metasurface is something which is emerging. So what is this holographic metasurface transceiver is? This is basically a passive continuous phase shift elements that is attached to your transmitter. And now you can control the phase shift offered by each of these elements here to steer your signal in a particular direction. So if we are able to appropriately steer in the direction, in the desired direction, maybe this will improve the coverage as well as the rate of the wireless communication. And moreover, these are like just the passive devices. Maybe because of that, these are like easy to manufacture, and also the power consumptions could be a lot lesser here. So because of that, these are actually potentially considered as like next in the 6G, some kind of like similar to reflecting surfaces, how this could be used to improve our network performance. Okay, so obviously when you want to get the best received signal strength, you need some channel state information, and getting that is not always easy. So people have proposed different methods for that. Like I have just listed something, maybe based on exhaustive search, maybe compressed sensing, and some recent algorithms based on, again, this hierarchical search. But these algorithms may be sometimes hard because of their requirement of computational aspects, and there is a requirement that some simple algorithms can somehow help us steer the beams in the appropriate direction. And that is where this study comes. How one can learn the proper direction in which I want to steer my signals without having much information about the CSI, or like put alternatively, how can I do this with minimum amount of information? So the objective here is to develop a learning algorithm that learns the optimal shifts from the received pilot signal in a noisy environment. So by the way, notice that when we say this HMTs, right, they are coming with a lot of phase shift elements. Now, and I mean, there could be very large amount. If you want a very granular steering, you want actually a large number of phase shift elements. But then the question is like, yeah, how to identify the phase shift for all these elements, and how it may work. So that is the question we are trying to ask or answer in this part of the part. Now, a little bit more on the structure of this holographic metasurface transceiver. Like here, this HMTs consist of these phase shift elements. Maybe each have some dimension, but that could be very arbitrarily small. In fact, we can think them to be forming this are like a continuous. And they will be directly connected to your transmitter, and they would be fed with this RF generator. And the the job of this HMT is to steer the signal generated by RF in a particular direction. And again, as we discussed in the mmWave, here also comes the case of line of sight path and non-line of sight. But again, we will focus on the line of sight path here. Okay, let me see. Okay, some notations in this slide. Let's say that I have my HMT surface here and there is an user here. Okay, and I'm going to consider any point here, let's say one point here, which is I'm going to denote as mx and my. Okay, so there is a phase shifting element here at location mx and my, and I'm going to assign a phase shifting weight of beta mx and my there. And these are the phase shift elements that I want to control, so that when I feed my RF signal into this HMT, they get very high, they are received with very high strength at the user. So this beta mx my, these are the phase shift elements, and the d naught here is the distance between the user and the center of HMT, and this f mx my, this is something, the channel property, this is the, and also this HMT itself, this is captures the effect of the size and power radiation pattern of the phase shifting elements. And in addition, this theta and phi, these are the elevation and azimuth angle my user makes with the HMT. Okay, so all these factors govern what is the received signal strength that I'm going to achieve at the user. Okay, now this problem we are going to consider little simplified version of this, and that simplified version actually applies when we are considering a far field model. First of all, this parameter I said f mx my, we are going to assume that this is going to be the same irrespective of what phase shift element you are considering. And naturally, if the my user is at a far distance, maybe I can interpret that at every phase shift, this parameter is the same. And then I am going to consider this linear model where instead of separately defining what is the weights at point mx and my, I am going to define through this function here. Okay. Now for every mx my, notice that by parameters beta 1, beta 2, I'm going to now assign what is the value of the weight. So this is the model we are enforcing. In the way we are going to assign weights to the weights to each of the phase shift element, and it is shown that if you are going to enforce such a model, then the gains that the user going to see is actually expressed by this expression, actually given by this expression. So I will not go into this because this is being derived in the paper which I have highlighted here. This is based on a lot of physics aspects. But what helps us is, notice that now all that matters to me, the gain that matters, that I'm interested in is now parameterized by these values beta 1 and beta 2. And now whenever this function is maximized for a pattern beta 1, beta 2, if it is maximized for certain beta 1, beta 2, that means that will guarantee a good gain at the receiver, and I can use those beta 1, beta 2 and accordingly set my phase shifts. But this entire expression, if you notice, it depends on parameter alpha 1, alpha 2, which depends on elevation and azimuth of the user with respect to HMT. And that we don't know. We don't know the user location. So because of this, I can't right away optimize this unless I figure out what is the value of alpha 1 and alpha 2. And naturally, in fact, this is like a product of two sinc function. This is maximized when beta 1 equals to alpha 1 and beta equals to alpha 2. So if I have to maximize this, this is as good as knowing the user location, which I don't know. Okay. So now the whole problem boils down to, is there a way that I can figure out what is this alpha 1 and alpha 2? Now we will see that how again the UB3 algorithm that we discussed can be applied here. So this is the 3D graph of the gain that I put in the previous slide. We have depicted here. You see that this is like a multimodal function. You see multiple lobes, and the lobe at the center has the highest signal strength. And as I said, this function is maximized at the points where beta 1 star is alpha 1 and beta star is alpha 2, and where alpha 1 alpha 2 depends on the user location, which I don't know. But instead of looking into, and by the way, like these values, alpha 1 alpha 2 can be continuous. And this alpha 1 and alpha 2, this is a product of sine and cos, so that they can be anything between -1 and 1. So now I am facing a problem where I need to identify this alpha 1 and alpha 2, which are continuous, and they can lie anywhere between -1 to 1. So to overcome this, what we'll do is we will discretize this problem by fixing one of the parameter at a time. So what we can do is, by the way, notice that here, this is a product of two sinc function. But if you fix one of this parameter beta 2, this is just like a one sinc function. Okay. Now you fix, maybe like, let's say fix beta 2 first. If you fix beta 2, now this is like a sinc function. Okay. Now this sinc function, if you discretize it an appropriate point, like here, these appropriate points are given. I will not go into that. That is a little straightforward to see, but it needs some working out the details. If you choose certain discrete point, whatever the remains is actually unimodal function. Even though it may happen that the peak of this continuous function may not coincide with the peak of your discrete values, but the values when I look into the discretized space, that is like a unimodal structure. So now this gives me some way to go ahead. Instead of worrying about searching over the entire continuous space, now I can think about searching over a discrete space. Maybe there will be loss in throughput a little bit, but maybe that is not too much. So one thing to note here is that if you are going to fix, let's say B2, and you are going to discretize with respect to the parameter beta 1, the set of the mean rewards you are going to get, that means that is going to satisfy unimodal structure. Okay, so I will not go into that. This is a little dense slide. The point is, yeah, once we discretize, we can look into the mean received signal of those discrete points and then take the mean values of that and try to learn the mean values of those discrete points. So now we can use our fixed budget pure exploration setup here. We can discretize the values of beta 1, beta 2, but fixing one at a time. And we can do this over a given period of time by giving equal slots to both of them, like when I fix one parameter and when I fix the other parameter. And the policy is the same as earlier, like it has to decide which arm to select given the past observation. Now at the end, the algorithm will do such that when I, let's say, fix beta 2, when I'm discretizing and learning over my beta 1s, it is going to give at the end of t by 1, t by 2 rounds, it is going to recommend one arm. And after that, I am going to fix this arm for the beta 1 and now discretize over beta 2. And I will, at the end of the t by 2 rounds, whatever it recommends, I'm going to take it. Now, my objective is to ensure that what is that policy, which is making sure that in both of them are not the incorrect arms. Okay, so this is the probability I'm interested that both in the discrete arm, I'm identifying the optimal arm in both for the beta 1 as well as beta 2. Now the algorithm is pretty straightforward. What we are doing is, given time period t, I will divide it into t by 2, t by 2. In the first part, let's say I will fix beta 2 to some value, whatever I want, I can fix here. And then I will simply invoke my two-phase UB3 algorithm. The UB3 algorithm is same as earlier. It will run for t by 2 rounds, and then it will output its recommendation. And after that, in the remaining t by 2, I will fix the beta 1 value to whatever is recommended by phase first part, and then do the same thing and get the recommendation for beta 2. Okay, and once I have this beta 1 and beta 2 through these algorithms, now I go back to my linear model and get the phase shifts for each of the elements in my HMT. Okay, so let me see how much is the time. Yeah, I think we are almost close. Here are some numerical evaluations of this algorithm. As I said, there are already these algorithms which are exploiting unimodal structure in the case of cumulative regret, and this line search algorithm is also exploiting unimodal structure, but this is doing it in a high confidence sense, not in the fixed budget sense. We have compared our algorithm on this and some of the recent algorithms. Again, these figures are cluttered. I will not go into that, but what I want you to note is the performance, the summary of the performance of our UB3. So this UB3 identifies the best phase shift parameters with more than 80% probability within about 200 rounds. While within the same number of rounds, others can only guarantee the current one with 45% probability. So in a way, like ours is giving with a much higher probability the correct arms. And sequential halving needs at least 250 number of time slots to complete one phase, whereas ours takes much lesser number of rounds. And all of this being done under various settings by varying the power levels, by varying the distance, and this performance remains consistent across varying different parameters. Okay, and these are another set of curves where we are checking, we are on the x-axis, we are changing the number of pilots we are going to use and achievable rate on the y-axis. Here again, our algorithm. So this is our algorithm. We forgot to rename it. So the two-phased UB3, it improves the average throughput by more than 50% compared to HBA and by more than 30% compared to the HOUCP algorithm when we look into the 500 duration as the fixed budget. Okay, so overall, in the fixed budget setting, UB3 is able to exploit the unimodality better, and that is why it could guarantee the optimal arm with very small error. Okay, so in conclusion, what we did in this talk is we looked into the beam alignment problem of millimeter wave system as using fixed budget pure exploration map setting, especially exploiting the unimodal structure. So it's not that fixed budget pure exploration has been not used in the to exploit the unimodal structure. It has been used in the confidence setting, but as we discussed in the wireless setting, maybe fixed budget is more appropriate from the protocol design point of view, and our work actually tried to address that issue. So we give upper bound on the algorithm that we developed, which exploit this structure, and we argued that its actually error probability is tighter than the other ones which don't exploit the unimodality structure in the fixed budget setting. And the simulations validated that this UB3 outperform other state of the algorithms. And we said that how this UB3 algorithms could be used in other applications of wireless networks like HMT, that holographic meta transceiver, where unimodality structure again naturally arises, not in an explicit way, in an implicit way. So there are, unimodality is not something alien to wireless networks, right? We have seen that most of the throughput curves follow this unimodal structure. So what we are proposing is, yes, we could exploit that in the fixed budget setting. Okay, so with this, I will conclude my talk, and thanks for listening. So these works have been already posted on the archive. If you have any follow-up questions, we will be happy to take. Thank you. So if there are any questions on this, I'll be happy to take.
I have a question.
Sure.
Yeah, so the recent simulation results that you showed in the case of HMT, what is the number of elements that you have used? The whole HMT, how many elements are there?
We did not mention that. Let me see if it is there. Sorry, I don't know that. I need to follow up with my student on this.
Was it there in the previous slide?
Oh, maybe in the table, you mean?
Yeah, I think that was it.
Okay, I see. So we are considering the dimensions, like the width. Lx is the width of the HMT, and Ly is the length, right? And each one having a height of dr.
Okay. Yeah, because only one query I had to ask is, so you have shown the simulation results for a fixed budget of 200 rounds. Now, suppose if the number of elements itself is of the order 200, then I can as well do the conventional channel estimation instead of going for a beam alignment based strategy. So that's where I wanted to get some more clarifications.
Okay, I see. Yeah, the whole point here is our assumption is the phase shift elements are going to be large. And that is why we are reducing the estimation of the phase shifts to few parameters. So one more thing I can check is, okay, I have, so this mx is going to be Lx by dr, 1 by, and this dr is in the wavelength, which is in the milli. I feel that like, yeah, so by this rough calculation, the number of phase shift elements we might have considered more than 1,000.
Okay.
Yeah.
Thanks.
Thank you. We can take a few more questions.
Chat. Chat. No, I don't see anything in the chat.
Thank you again, Professor, for the talk. The link to the slides will be posted on our webpage. Thank you and have a great day.
So should I share these slides or?
Yes, sir. You can email us.
Okay, fine. Thank you. Thank you, everyone. Thanks for attending. Bye.